am teacher Sobian, physics teacher from SMK KRIAN. Learning standard. At the end of lesson, students are able to explain wave-particle duality. Success criteria. Students are able to introduce de Broglie hypothesis to explain wave behavior of particles using the relationship between momentum, particle behavior, and wavelength, wave behavior. Conclude how de Broglie wavelength change with mass of particles and velocity of particles. Describe application of wave behavior of an electron in the operation of an electron microscope based on de Broglie wavelength. Compare image produced by electron microscope and light microscope. Is light wave or particles? According to the wave-particle duality, light possesses both wave and particle properties. From the previous lesson, we know that electromagnetic radiation such as light is said to have wave properties because it exhibits the phenomena of diffraction and interference. Objects like marbles are said to have particles property because they possess momentum and kinetic energy and can collide with each other. Here is a table showing which phenomena can be explained as waves and particles. Louis de Broglie introduced the hypothesis on the wave nature of particles in 1924. Einstein and de Broglie postulated the idea of wave-particle duality of light and all subatomic particles. In 1924, Louis de Broglie, a quantum physicist, had put forward a hypothesis stating that all particles can exhibit wave characteristics. He stated that the relationship between the momentum of a particle and its wavelength is as follows. Lambda equal to h over p, where lambda equal to wavelength, h equal to Planck constant, and p equal to momentum of particle. The greater the momentum of the particles, the shorter the wavelength. Since the value of momentum of particle can be determined by P equal to mv, the following formula can also be obtained. Lambda equal to h over mv, where m equal to mass of the particle and v equal to velocity of particle. Since the value of h is very small, particles of large masses will have de Broglie wavelengths which are too short to be detected. Therefore, the wave characteristic cannot be observed. If electrons consist strictly of classical particles, and these particles were fired in a straight line through two parallel slits and allowed to strike a screen, we would expect to see patterns corresponding to the size and shape of the slit. However, when this two-slit experiment is actually performed, an interference pattern emerges when these particles are allowed to build up one by one. Thus, electrons also behave like waves. In 1927, the presence of wave properties of electrons was confirmed through electron diffraction experiments. Here was the result from the experiment. Photograph 7.1 shows diffraction pattern of electron through a thin layer of graphite. This pattern resembles the light diffraction patterns of red laser light through an aperture as shown in photograph 7.2. So this confirms Du Bois hypothesis. The Du Bois wavelength of electron beam is approximately 1000 to 10,000 times shorter compared to the wavelength of light. This property is very important for higher magnification of electron microscope. Now, we will observe a video regarding the application of wave behavior of an electron in the operation microscope based on the de Broglie's wavelength.
Scanning electron microscope. The scanning electron microscope, also abbreviated as SEM, is an instrument that produces a largely magnified image by using electrons instead of light to form an image. A beam of electrons is produced at the top of the microscope by an electron gun. The electron beam follows a vertical path through a microscope, which is held within a vacuum. The beam travels through electromagnetic field and lens, which focus the beams down toward the sample. The beam passes through a pair of scanning coins or a pair of diffractor plates in the electron column that diffract the beams in X and Y axis. Once the beam hits the sample, electrons and X-rays are ejected from the sample. Detectors collect these X-rays, backscattered electrons and secondary electrons, and convert them into the signal that is sent to a screen similar to a television screen. This produces the final image.
A comparison between the image produced by optical microscope and electron microscope. A is an image of red blood cells under an optical microscope, and B is an image of red blood cells under an electron microscope. In conclusion, the wave-particle duality means that each particle can exhibit the property of particle and wave. Electrons are said to have wave-particle duality because they exhibit the properties of both particles and waves. Light also possesses both wave and particle properties. Light is said to have particles properties because it exhibits the phenomena of photoelectric effect. Therefore, light and electrons are said to have wave-particle duality. This duality is also found in all kinds of radiation in the electromagnetic wave spectrum, as well as in subatomic particles like protons and neutrons.